As the world races toward a post-fossil fuel future, electric vehicles have become the poster child of clean mobility, but they may not be the final answer for every road, load, or climate. While battery-powered EVs dominate headlines and investments, Germany is quietly hedging its bets with a parallel track: hydrogen-powered engines. Through aggressive funding, pioneering prototypes, and strategic industry collaboration, the country is reimagining transportation with a focus on hydrogen technology. This is no hyperbole. Germany's new hydrogen engine technology will destroy the entire EV industry forever. Well, at least that's the plan. Let's see how it will work out. Germany's hydrogen engine developments. Back in June 2020, the federal government of Germany unveiled its national hydrogen strategy, allocating €9 billion to accelerate hydrogen production, distribution, and application across key sectors. Of this, €7 billion was earmarked to stimulate the domestic market and industrialize green hydrogen technologies, while €2 billion was designated for fostering international partnerships. The strategy marks a significant pivot in Germany's long-term climate goals and is directly aligned with broader EU objectives, including the European Green Deal and the Fit for 55 legislative package, which targets a 55% reduction in greenhouse gas emissions by 2030 compared to 1990 levels. Green hydrogen, produced via electrolysis powered by renewable energy sources like wind and solar, is central to this initiative. Unlike gray or blue hydrogen, which involve fossil fuels and carbon capture, green hydrogen offers a carbon-neutral path for decarbonizing hard-to-electrify sectors such as heavy industry, logistics, and long-haul transport. A key target of Germany's hydrogen roadmap is the mobility sector, where the limitations of battery electric vehicles, particularly in range, charging times, and suitability for heavy-duty use, create space for hydrogen technologies to thrive. German automakers are leveraging hydrogen to future-proof their relevance in a rapidly evolving market. BMW, for instance, has emerged as a leader in the hydrogen mobility space through its development of the 9.5 Hydrogen, a fuel cell electric vehicle or FCEV based on the existing X5 SUV platform. The vehicle, first revealed at the IAA Mobility Show in Munich in 2021, is the result of a long-standing partnership with Toyota, which supplies the core fuel cell stack used in the prototype. The 9.5 Hydrogen has a range of around 500 kilometers, refuels in under 5 minutes, and emits only water vapor. BMW began producing a small series of these vehicles in December 2022 at its pilot plant in Munich for global demonstration. Beyond fuel cells, BMW is also investing in hydrogen combustion technology, known as H2ICE. Unlike fuel cells, which convert hydrogen into electricity via electrochemical reactions, H2I systems use modified internal combustion engines to burn hydrogen directly. This approach leverages existing manufacturing capabilities and could offer a more seamless transition for certain vehicle categories. In the commercial transport sector, MAN Truck & Bus, a subsidiary of the Volkswagen Group, is spearheading hydrogen combustion engine development for heavy-duty logistics. MAN's upcoming hydrogen trucks are designed to address the energy demands and operational patterns of long-haul freight, where battery weight and recharging times pose significant barriers. In March 2023, MAN announced it would begin real-world testing of its H45 hydrogen combustion engine in partnership with key logistics providers by 2025. The engine uses port fuel injection with spark ignition and operates with zero carbon dioxide emissions when powered by green hydrogen, though some nitrogen oxide emissions still occur. These can be mitigated using standard exhaust after-treatment technologies. Simultaneously, Daimler Truck, the commercial vehicle division of Mercedes-Benz Group AG, is focused on fuel cell technology. Its flagship project, the Gen H2 truck, uses liquid hydrogen for improved energy density and greater range, over 1,000 kilometers per fill. Designed specifically for long-haul operations, the Gen H2 truck is being developed in partnership with Volvo Group, under a joint venture called Cellcentric, founded in 2021 to build large-scale fuel cell systems for trucks. Daimler conducted initial prototype testing in 2021, and full customer trials will follow, with series production planned for 2027. The use of liquid hydrogen, stored at -253 degrees Celsius, offers logistical advantages over compressed hydrogen gas, particularly for cross-border freight routes requiring extended range. In the background of all this innovation, Bosch, one of the world's largest automotive suppliers, plays a pivotal enabling role. The company is heavily investing in both fuel cell systems and hydrogen production technologies. In May 2022, Bosch announced a €500 million investment in solid oxide fuel cells for stationary applications, and another €1 billion through 2024 to develop and manufacture mobile fuel cell systems for vehicles. Bosch has also partnered with PowerCell Sweden AB and Ceres Power to advance its technological capabilities. Additionally, Bosch is developing hydrogen electrolysis systems to support green hydrogen production, with pilot projects underway across Germany and other EU countries. The company's involvement across the value chain, from production and compression to fuel cells and storage, positions it as a key player in scaling hydrogen adoption throughout Europe. If infrastructure and production costs can be brought in line with economic realities, Germany could lead in the global hydrogen economy. So, what is it that we're actually talking about? Let's dive deeper. Types of hydrogen engines. Hydrogen-powered vehicles fall into two primary categories: hydrogen fuel cell electric vehicles, or HCEVs, and hydrogen internal combustion engine vehicles, or H2ICEs. While both rely on hydrogen as a fuel, they diverge in how it is converted into usable energy. HCEVs convert hydrogen gas into electricity through a chemical reaction with oxygen inside a fuel cell stack. This electrochemical process, known as reverse electrolysis, produces electricity, water vapor, and heat as byproducts. The electricity powers an electric motor, which drives the vehicle, just like in traditional battery EVs. However, unlike EVs that draw power from large lithium-ion batteries, HCEVs generate electricity on demand from hydrogen stored in high-pressure tanks. The architecture typically includes a smaller lithium-ion battery or supercapacitor to handle peak power demands and regenerative braking, but the primary energy source is the hydrogen fuel cell. A leading example of FCEV technology is the BMW 9/5 Hydrogen, a hydrogen-powered variant of the X5 SUV. It features fuel cell stacks supplied by Toyota, which has over a decade of experience in hydrogen mobility through its Mirai model. The 9/5 Hydrogen achieves a range of around 504 kilometers or 313 miles under WLTP standards, with hydrogen tanks capable of refueling in under 5 minutes, providing an edge over battery EVs in terms of turnaround time. Another global benchmark is the Hyundai Nexo, which offers a similar range and has been available commercially since 2001.